All right. First things first, I marked your markdown files. They looked great. So nice work. So far, everyone has 100% on the assignments. Feels good, right? So, so that was good. I'm pleased with that. And we'll do kind of more lab stuff, I'll call it, on Friday when we work through the Explore section of the R for Data Science page. Now, if you haven't had a look, right, it might be helpful if you kind of click through it and kind of skim through it before Friday's class. If not, I'll be walking you through a lot of it anyways, but we only have a little bit of time, right? So helps if you've kind of read ahead a little bit. Okay. And that's that link that I posted at the top of the Moodle page. Okay. Let me see here. I need a pen. All right. Where did we leave off? I feel like it was on histograms, right? So we were talking about histograms. Okay. And we said that a histogram, and because I have this on the previous notes, I'm not going to bring them in. I'll bring in this little blurb here. But the histogram helps us visualize the distribution of a numerical variable. Okay, so just for some quick review. Now, I'm not going to review everything that we did last day. I'm just going to review what we left off on because hey, so many faces, so fun. So just because it was just on Monday, so it should be relatively fresh. And you have the notes. We use histograms to visualize the distribution of a and now I'm blanking on, all my different courses are using different terminology, and I'm trying to stick with the same terminology as the textbook. Are we using numerical or quantitative? I feel like we're using quantitative. Yeah. All right. Of a quantitative variable, right? But just as a reminder, right, I might call it a numerical variable because I might slip up every now and then, right? And so we use histograms to visualize the distributions, and we're looking at things like the shape mostly, which is what we're going to talk about next, but we're also talking about the center, so where are most of the data located, right? And so we look at the shape, the center, and the spread, typically. Okay. So we'll start by talking about the shape, and then we'll talk about the center, which is really just asking where are most data located. And then the spread, right? And then from that center, how much of a spread are we expecting to see? How much variability is there, right? So how much variability is there? Right, is kind of what we're looking at, okay? So I'll bring in that histogram again. Why not? Okay. So in terms of the shape, we're going to talk more about the shape because we're looking for some key things. We're looking for symmetry, which is later going to evolve into a normal distribution, right? And so for the shape, we can have symmetric, which is later going to be maybe a normal distribution. Okay. Symmetric about the center, right? So symmetric, and then I should say, oops, around the center, right? Or it can be skewed. Okay. If a distribution is skewed, it means that a lump of the data is in kind of one location, and then there's a long tail in one of the other directions, right? So that means that we don't have symmetry anymore. Okay, and so this is where I'm going to pick up, I'll call that the end of the review, but it's sort of like a review with some new stuff. That was a weird review. Anyways, it's all the things I wanted to say last day, but didn't. How about that? So if we're looking at, I'll bring in this little note here first. If we're looking at these distributions here, okay, how can I? What we have, and I'm going to zoom in here, let it catch up. Okay, so here, right, if I had to kind of have a gatekeeper, I would say, is this symmetric, yes or no, right? And so when I look at this, this is not symmetric, right? I can't fold it in half and have it look the same, right? And so here, this is not symmetric. And so we can kind of leave it at that for now, right? And same thing here, this is also not symmetric. This is exactly symmetric, fortunately. It's not usually exactly symmetric, right? But here we've got this beautiful kind of very symmetric distribution. And so what it ends up looking like is, so here, these bars are just data, right? So you have to kind of, in my case, take your glasses off. Well, I had laser surgery, so it doesn't work anymore. But I used to have to take my glasses off and just kind of, you just need to look at the general shape, right? And so if we're looking at the general shape of this thing, it might look something like this, right? Just in general. Same thing here, right? We might have something that looks like this. Whereas here we have kind of something that looks like this. And then here we might have something that looks like this. Okay. So general shapes here. This is symmetric, right? And it also has this beautiful bell shape. So we call this a normal distribution, right? And so for the shapes, the normal distribution looks like this. This is the normal. Sometimes I'll capitalize it because it's a name, right? So, and it kind of gets confusing because it is the most common distribution, most common naturally occurring distribution in pretty much anything that we measure. But in business, when we're dealing with money, we often see skewed distributions. So that's why we need to talk a little bit more about skewed distributions in our case here. But in general, the normal distribution is kind of our go-to, and it happens a lot in pretty much everything, heights, grades, usually. Why can I only think of two things? Speeds, distances, whatever, right? And so the normal distribution looks like this. So it is symmetric, but it also has just one peak, right? And so the normal distribution is symmetric with one peak. Later, I might call it one mode, but we haven't introduced that yet, so I'll call it a peak, right? But one high point. Okay. And so when we're looking at a histogram, right, the reason we look at the distribution is to identify if there's any skewness, right, or lack of symmetry. So like I said, if you're looking at a distribution, so if you're looking at a histogram, and the first thing I want you to look for is it symmetric? Yes or no, right? If it is symmetric, then go ahead and see it's probably a normal distribution, right? If it's not symmetric, then we need to talk about the skewness, okay? And so the skewness is a little bit counterintuitive, I think, at least, because if we could just kind of zoom in here, right? This says that this is moderately skewed to the left, right? And I don't know about you guys, but for me, when I look at this, I naturally want to talk about where most of the data is. No, right? What's going on here? It's skewed to the left. So we're talking about the tail, right? And so it's always skewed in the direction of the tail. And we're going to find that a lot, especially in statistics, is that we're always concerned about those extreme values, right? What are those rare values that can happen, right? They're over here in this left tail versus over here in the second one. Now the tail is going to the right. So now it's skewed to the right because this is where we have these kind of more interesting values, right? We don't really care about where everyone is, right? Oh, we've got some interesting cases over here. So that's why we say it's skewed in the direction of the tail. Okay, so we can go through kind of moderately skewed, right? So here I would call these moderately skewed, just like the textbook does. And then we might have something that's highly skewed, right? So where you have this really long tail. I'm noticing I really lifted off here. Should have made it more obvious. I'm going to do that. Whee. Oh. Something like that. Right. And so, but in either case, right, it's skewed in the direction of the tail. Okay. So I want you to notice the distribution is always skewed in the direction of the tail. Okay. That's important. It throws people off, right? I want to talk about these guys here. No. Talk about the tail, right? So it's always skewed in the direction of the tail. Okay. Things like income. So as soon as you're involving money, typically you have this really quite right skewed distribution, right? So if we're talking income, a lot of people are going to be kind of here in the lower ranges. And then as we get up into the higher ranges, right, that's where we want to be. But it's hard to get there, right? So then we have these kind of smaller but long tails, right? And especially because you can't make less than $0, let's say, per year, right? And so there's going to be a cutoff point at 0. And that usually means that you have some sort of skewed distribution. Same thing with grades. Now, typically grades do follow a normal distribution. And, for most classes, probably centered around 70%, right? So you've got this kind of symmetric curve. Most people are hanging around 70, 75, depends on the course, right? So ask me if I've looked at my distributions for my grades. No. I teach it, and then I don't look at it myself. Oh well. So I actually don't know what my grades look like, but that's okay. So grades, right, we're ranging from 0% to 100%, so we are limited there. And so if we have really, really high grades, for example, then most people would be up here, kind of pushed up against here. And then we end up with this left skew. Okay. All right. Good, good, good. When we talk about centers, right? So instead of eyeballing the center from the histogram, we're going to have numerical measures of center and a few different versions. And so that's in the next section. So we're going to parking lot that as well as the spread. Okay. But we can see a lot of it from the histogram. Okay. So before we keep going, I want to talk about just a little bit about cumulative distributions. Now, cumulative, you've probably heard the word cumulative, right? Because the final exam is cumulative. What does that mean? It means everything up to that point, right? In terms of the final exam, it means everything that's been covered up until that point. Same thing goes for cumulative distributions, right? How much of my data have I seen at this point, right? I would have seen this bar as well as this bar, right? How much of my data have I seen up until the midpoint for a symmetric distribution? I've seen 50% of the data, right? Assuming that it's symmetric and I'm halfway through, right? Then at the midpoint, I've got 50% below it, 50% above it, right? And so let's see here. We can look at just some values here. Copy, 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 copy. I think we developed these numbers, or we didn't develop them, but I feel like I got one of them. Let me just confirm here. We talked about this last day. Can't remember. It's just on Monday. I can't remember, but I think we did, right? And so we had these bins for the audit times, and then we had the frequency in each bin, right? And so what we can look at is instead of 10 to 14 days and then 15 to 19 days. Oh, I remember, because you can't have any overlapping categories. So I did talk about it. No overlapping bins. Aha. And I even confessed, I think, to having messed it up at work one time. I had to redo it all. Oh well. 19 to 20, 24 to 25, 29 to 30, right? And so now when we're talking about cumulative distributions, right, we can talk about, okay, less than 14, right? There's a frequency of 4, but now this is going to morph into less than 19 days, right? Less than or including 19 days. Well, that's going to be 8 plus 4, right? So a frequency of 12. So as we keep going, we add the previous frequencies, which we'll see here, right? And so that's where that 12 is coming from, right? It's because it comes from 8 plus 4, right? And then I guess I could figure it out, but I'm just going to copy from here. I'm going to steal it. I'm a thief. 4 plus 8. This one is 4 plus 8 plus 5. Gonna run out of room. 4 plus 8 plus 5 plus 2, and then the last one is all of those plus 1. 4, let's see here. 4 plus 8 plus 5 plus 2, and this one is 4 plus 8 plus 5 plus 2 plus 1. Now I don't need this one anymore, so I'm going to ditch it. I got what I wanted. I got these numbers, right? And so here, when we're talking about the cumulative frequency, that's fine, right? But we know that we have a total of 20 audits that we looked at, right? So we looked at 20, a sample size of 20. And so usually what we do is, instead of talking about, oh, 4 out of 20 or 12 out of 20, because again, that's hard for us to wrap our head around, right? We convert it to relative frequencies, right? So decimals, or if you want to multiply by 100 and talk about percentages, that's totally fine too, right? And so 4 out of 20 is 0.2 or 20%. 12 out of 20 is 0.6 or 60%, and so on and so forth. So I'm going to show you where this came from here, but this is 4 out of 20. And this is 12 out of 20, right? So it's doing the same thing, but it's just relative to the sample size, right? And so here, the sample size is n equals 20, which should be the same thing as the cumulative frequency at the last bracket, right? And of course, should add to 1, right? Probability of 1 or a proportion of 1 or 100%. Otherwise, we've missed something along the way, right? Good. Okay. Sorry, I got caught in a loop here. 20, 60, 85. For a second, I thought that they should add up, but no, because they come from these cumulative frequencies. Yeah. Okay. Convinced myself. Maybe not you guys, but I convinced myself. All right. So, good. We don't use tables that often for numerical data because it's easier to just visualize it, but it's good to have seen it at least. All right. So now time for a moneymaker here. We'll do this whole kit and caboodle. Hopefully it works out. All right. Okay. So when it says measures of location, location in terms of where is most of the data located, right? And so I want to put that here because that wasn't obvious to me. I would probably say measures of center, right? But measures of location, location is where most data are located, right? We could, oops. We could call it the center. I think the reason that they're hesitant about calling it the center is because if we have a crazy skewed distribution like this, then visually the center might be somewhere here, right? Whereas maybe the location of most of the data would be here, right? So the location of most data might be kind of in this range, right? But the measure of center or the actual center of this data might be here, right? And so I think that's why they're not using the word center, but if it helps you to think about it as the center, then that's fine by me. That's probably what I'm gonna do. Right. So, but this is kind of the reason why they're calling it location instead of the center. Okay. So the mean is the average. Okay, we could specify and call it the arithmetic mean, but usually we just call it the mean, and then later we'll talk about the geometric mean. If we're using the geometric mean, we're always going to call it the geometric mean. And so if we just say the mean, we mean the arithmetic mean. Okay, so the mean is the average, right? So I'm feeling pretty confident that you already know how to calculate the mean, right? If I give you 10 data points and I ask you to find the average, what would you do? You'd add them up and divide them by 10 because there are 10 data points, right? And so you know how to do that, right? And if you're working with huge data sets, you don't want to add them up by hand. That sounds terrible. But of course, Excel is probably the easiest way to quickly get the mean out of a data set, of a larger data set. I'd say anything larger than like 15 points, even 15 is too many to do by hand, in my opinion, because I'm lazy. But you could do it, I guess, if you want to. But I'd probably just throw them into Excel and make Excel do it. I think even you don't even need to use a function in Excel. I'm pretty sure if you just highlight all the data that you're interested in, doesn't it tell you the average at the bottom? I feel like it does. It gives you the sum at least, and then you and the number of data points. Either way, right? So
yeah, it will give you an average on you. What did
it does give you an average?
Yeah.
Nice. See, we don't need to calculate it. Well, we need to calculate it, but not by hand. It's insane.
Yes.
Yeah. We need it. We need it a lot, but we don't need to calculate it. Okay. And so the mean is the average. We know how to calculate the average, right? And so that's not the hard part. I'm not sure how comfortable you guys are with summation notation. Hey, I wish it had kept up with my Anyways, when I say summation notation, you say, yeah. No.
Yeah.
Yeah. Are you guys feeling comfortable with summation notation? Yeah. Or no?
Summation notation
Is okay or bad?
Yeah, that's for me. I don't know for you.
Okay. If you're not feeling 100% comfortable with summation notation, it's going to come up. But because we're not going to be doing any calculations by hand, it's just something to kind of, oh, okay, I add things up, right? So when it says X bar, which I want to talk about. But when it says the sum, so a capital sigma, that's the sum of X subscript I, it means add up all your X's, right? And X is usually used to denote a data point, or in general, a data point. X1 is the first data point. X2 is the second data point, up, 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 until you have Xn, because n is your sample size, right? And so until you've reached your last data point, right? And so here, X subscript 1 is the first data point. Whatever its value is, X2 is the second, and X subscript n is the nth data point. And recall, n is the sample size, right? And so whatever your sample size is, you have to add them all up, right? And so when we see the sum here, you can kind of ignore the I, it just says add up all the X's, right? And then divide by n, which again is your sample size. Okay. Of course, you can use the average function. I think Excel uses the term average, pretty sure. Always throws me off. I always type in mean and expect it to give me something, and then it only comes up with the median. So then I have to average. So, yeah, should call it the mean, but they call it the average. I'm fairly certain. Huh?
I agree.
Yeah. So, so this is really just saying add up all the X's. Okay. All right. So X bar in general, X we use to denote a generic data set. So whatever data set we're talking about, we usually use X. And then if we have another data set, we might call it Y. And then if we have a third data set or a third variable, maybe we might call it Z, right? So on and so forth, just to keep things straight. But the X bar and X bar is the mean of X. And maybe I should use a similar X down here. I like to throw a little curve on there. Otherwise, sometimes and you're not going to believe this, but sometimes X's and T's end up looking the same. It's weird. You can see them morph into each other. But especially if you don't have the bad. So I try to have a little spin on there, and it's fun to write. So so for my X's, X bar is the mean of X, but really whenever you have a bar, it's not just the mean, it's the sample mean. Yeah. Remember, one of the tricky parts with statistics especially is we have sample information, but we're also trying to learn about the population, right? And there's population information, right? The sample is going to have some average. The population is going to have some average, right? And so we need notation to keep those straight. And so what we do is we use a little bar over our X or our Y or our Z, and that's to denote the sample mean, right? And so anything with a bar over it denotes a sample mean? Okay. How are we going to denote the population mean then? Right? We're going to use mu, the Greek letter mu, and I've got it over here. You'll see in these notes that I posted, there's these little sub notes. They're not going to come up, but it felt weird to exclude them because it's talking about, okay, so here's the sample data. That's what we have, and that's what we're going to do calculations on. But let's say that you have a population. There are instances where the calculation changes ever so slightly. Okay, and so then, I couldn't exclude them, right? But I can't remember if I copied this already, but there we go. So I've put them over here on the side. You can ignore them until I say so. You can ignore them. So, oh yeah. Usually when I teach this, anything with a bar over it denotes a sample mean. Have I done the average smiley face yet? Can't remember. How would you write the average smiley face? Average smiley. I just like that one. You can put a bar over anything, make it the average, right? You could even put a bar over a word if you wanted to, instead of using X and Y and whatever. But as it comes up, right, we might get jiggy with it. But for now, that's my favorite. It's your average smiley face. It's got an extra lip or an extra like grin. All right. So if the data set is not a sample, but is the entire population, right? And so we're going to use capital N to denote the population size, right? And so here, capital N is the population size. I feel like we've already mentioned that, but anyways, here it is. I'm teaching like sort of the same stuff in all my courses right now. It's like the beginning of the term, so we're laying all the groundwork, and then we're going to take off in different directions. But right now, it's really confusing for me. So that's why I'm not sure if I've said it already. I can't use my jokes twice. Only once per class. So then the population mean, we use mu, right? And so mu is going to be just what we use in general. And mu is a Greek letter, right? And if you wanted to, instead of typing it out, I'll show you how to typeset it in Markdown so that you can just type mu. But for now, if you just want to write mu, that's fine too. That's how we write it phonetically, I guess. Okay, and so mu is the population mean. Yeah. In general, what we're going to find is that we use kind of, is it Roman letters? What's our usual alphabet? I feel like it's Roman letters, but just a regular X, our alphabet. Someone Google quick. Anyways, I'm not very confident. anyways, our usual letters, those are going to belong to a sample, right? So whenever we're describing a sample with information from a sample, we're going to use kind of our regular letters, right? Whereas if we're talking about a population, right, so information from a population, it's very, very rare that we have the entire population to talk about, right? Usually what we're doing is we're taking a sample and we're doing calculations on the sample. And so usually all we're dealing with is sample information, right? But if we happen to have the whole population, what we have is parameters, they're called, but I shouldn't say that here. That's okay. They're called parameters, and they're denoted by Greek letters, right? So in general, we use Greek letters if we're talking about something from a population, right? And so any measurement from a population is typically, there's like one rare instance that I can think of where we don't, but we can ignore that and never talk about it again. Any measurement from a population is typically denoted by Greek letters. Okay, so that's a good kind of guide to keep these things straight, right? So these regular letters, that's from the sample. That's usually what we've calculated. So if you're finding that you're calculating something, it's probably going to be, you know, X bar or S for the standard deviation or something like that that's coming up. Okay, but it's good to keep those kind of straight. All right, so the sample mean, I'm trying not to talk too much about it, but there's a lot to say about the sample mean, right? And so the mean is our usual measure of center. It only really works as a true measure of center for normal distributions. So if you have a symmetric distribution, then the mean is the best measure of center. Okay. So if we have a normal distribution, the mean is the best measure of center. Yeah. So what's going to happen is you might have your distribution like this, and then what would happen is that the mean would cut it in half, assuming it's perfectly symmetric, and you can kind of bend it up, bend it in half. All right, so let's talk about some other measures of center before I keep going here. All right. I'm trying to cut it short because we don't need all that background theory about the mean, but I'm having a hard time. I know too much. No. Let's talk about the median. I feel like there was no, that's for that. All right. So the median is another measure of center. Okay, and so the median just says this is the value in the middle of the data, which means that we have to sort our data from smallest to largest if we're doing it by hand, which we're not. Right, so what it does is it sorts the data from smallest to largest, and then the value that's in the center is going to be the median. Okay? And so there's kind of a glitch, right? So with an odd number of observations, the median is the middle value, right? So if we pretend that we have some values here, let's say I'll sort them as I make them up. 3, 7, 9, 11. I gotta ditch this pattern. 12. Right? 15 and 21. Did I make an odd number of observations? Here we go. 1, 2, 3, 4, 5, 6, 7. Good. So what we would do is to find the median here, because it's sorted from smallest to largest, then I use my patent pending boop, boop, boop method. Very sophisticated. I take 2 fingers and I boop, boop, boop into the middle. And it works just fine if you have to do it by hand, right? And so here, 1, 2, 3, 1, 2, 3. So the median, oh, yes?
The median is 11.
Oh, sorry, I can't hear you. Oh, oh, I understand. Okay, thank you. So when it says an odd number of observations, right here, our sample size is 1, 2, 3, 4, 5, 6, 7. So here, n is 7. And so here with an odd number of observations, right, n is odd. So that's what it means. The values inside can be anything. Okay. Whereas, okay, I think I just confused everyone, maybe including myself, by only gravitating towards odd numbers. I didn't mean for that to happen. It can be anything. Okay. The tricky part is when you have an even number of observations, then there is no single middle value, right? And so if I extend this and I just add another data point here, then I might have something like 3, 7, 9, 11, 12, 15, 21, and 24, right? So now when I count in, right, I take my fingers. This is only for small data sets. Of course, you would probably use Excel or R, depending on how you've stored your data to find these, right? But just to show you the difference between the two, you put your fingers on the outside edges and then you boop, 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 boop your way in. And 1, 2, 3, 1, 2, 3. So what I do is I landed on both of these at the same time, right? So what I do is I take the average here. And that's weird, right? To find the median, we take the mean. It's true though. So the median is going to be 11 plus 12 divided by 2, which is 11.5, right? And so here, an even number of observations has no single middle value. That's what we found, right? So that's when we circle both of them. And then in this case, we follow convention and define the median as the average of the values for the middle 2 observations. Okay, and so that's how you find it. I am pretty sure Excel has a slightly more sophisticated method, right? So here, 11 and 12, they are kind of equidistant from each other, right? Or a splittable distance, let's say. If this was going from 11 to 24, or something crazy like that. I think Excel has a built-in way of dealing with that and shifts the median over one direction or the other, but I'm not entirely sure. But I know it's come up before, so that's why I'm just making mention of it. All right, so in this case, right, just to highlight here, n equals 8. So here, this is if n is even. Okay. Good. So the reason we would use the median instead of the mean is if we have a highly skewed distribution. Okay. And so we use the median. We use the median. Oops, I'll start over. We use the median as the measure of center for skewed distributions. Okay. So why do we think that is? Now, that's not something I'm expecting of you, right? But let's just talk about a little bit why that is. If this value, this 21, all of a sudden was 210, right? So something crazy huge, right? In terms of when we visualize our distribution, that means that we're going to have most of our data here between 3 and 15, right? So we've got data points over here in the low end, and then we're going to have a huge long tail to reach 210, right? And so when we calculate the mean, right, when we calculate the average of these values versus if we calculate the average where we replace 21 with 210, what's going to happen with the average is it's going to blow up, right? And so that's why the mean is only really useful if you have some symmetry, because the mean is always going to gravitate towards the tail, right? Those extreme values. Whereas the median, well, the median doesn't actually care what value this is, right? When we start counting in, it's just finding the central value, right? And so we call it a robust statistic because it's robust to extreme values. Okay, so we use the median as the measure of center for skewed distributions. The median is not affected by extreme values in the data. And I guess I should say, so we call it a robust measure of center. Feels weird. So we call it a robust measure of center. Okay. Just visually, what happens is if you have a skewed distribution like this, right, the median might be somewhere here. Okay, that's a pretty reasonable measure of center, right? Whereas the mean is going to run towards the tail, right? And so depending on how long the tail or how extreme those values are, let's show it as if it's really extreme here. Then the mean might be pulled that far off of the center. So now it's not really a good descriptor of the location of most of the data anymore, right? It's not really a measure of center anymore, right? Because we have a skewed distribution, right? And so the mean is always pulled in the direction of the tail. Okay. So that's just something to keep in mind. There are a lot of things that we could talk about here, right? If you are given the mean and the median and only those two values, right, you can get a sense of the distribution, right? If I tell you that the median is 10, for example, and the mean is 4, what would that distribution potentially look like? Well, first of all, because they're not similar, I know it's not symmetric, right? I also know that the mean is always going to get pulled in the direction of the tail, right? And so here I'll label this so it's not just floating around, but it might look something like this, right? Median is 10 and the mean, right? So just knowing the values of the mean and the median, we can have some idea of what the distribution is going to look like, right? And that's just kind of good for just off the cuff summarization, right? If you just have the values quickly, then first thing I do is I compare the mean and the median. And if they're similar, I can assume that I have a symmetric distribution, right? If they're different, then I know I have a skewed distribution and it's skewed in the direction of the mean. Okay. So we compare the mean and the median. Okay. And if they are, I'm going to say similar, right? They don't have to be exactly the same. There's going to be some wiggle room there. But if you're looking at kind of 10.5 and 11.1, I'd say those are pretty similar. So then I would argue that the distribution is symmetric, right? So we compare the mean and the median, and if they are similar, we have a symmetric distribution, right? If not, right, it's skewed in the direction of the mean. All right, that's enough on that. But any questions? I'm checking the chat, but everyone's just going with it, so. All right. So often people want to talk about the measures of center as the mean, median, mode. Okay, the mode is not that important. The mode is just where is the most frequently occurring data point. That's not that telling in most applications, but it is a measure of center, right? If you have multiple data points somewhere, right, then you have a mode. Okay, a mode in terms of the histogram is the number of peaks, right? And so I said, if it's a normal distribution, if you have a symmetric distribution with one mode, right? And so, or one peak. So in a histogram, the peak will be the mode, right? And so now we can develop the normal distribution is unimodal. Uni, remember, is just one, right? So unimodal is what we call it. Unimodal and symmetric. Right, and so it looks like this, and it only has one peak, one mode. We've seen that graph before, right? We've seen this. Okay, so a normal distribution, great. It has one peak, right? So it has one mode and it's symmetric. That's what makes it a normal distribution. But then what's fun about the normal distribution is that the mode, right, that peak, we also said that that's where the average is going to be, right? And so this is where the mean is for a symmetric distribution, because it's not being pulled in any direction, right? Because it's symmetric. And so it's being held in the center. But also, what's cool about the normal distribution is that if it's perfectly normal, if it's this beautiful normal distribution, then all the m's are going to be in the center. So the median is also in the center, right? If you're able to fold it in half, then half the data is below it and half the data is above that point. And that is the definition of the median, right? And so this is, oh, sort of looks like median, but I'll try again. Oh, it looks the same, right? And so unique to the normal distribution is that for a normal distribution, the center is the mode, it's the mean, it's the median, they're all the same, right? In terms of calculations, the mean is going to be the most powerful, okay? So we can calculate the mode, but the mode is really just the most frequently occurring data point, right? And so if we have a tiny little data set like this, 32, 42, 46, 46, 54, hey, they were hung up on even numbers. I was hung up on odd numbers. They were hung up on even numbers. I have two values of 46. So 46 is the mode in this case. Okay. It's possible to have more than one mode. Okay. And kind of a downfall of Excel, it seems like you have to use different functions. So there's the mode.single function if you're looking for a single mode. But if there happen to be multiple modes, I didn't include it here, but it's, I didn't post that. Shoot. I just finished it before class, so that's probably why I didn't post it. But I'll post the chapter 2 Excel cheat sheet after class. But there's another function that you have to use if you have more than one mode. Okay. It becomes a little bit useless if you have more than two modes. So usually if you have two modes, right, then you have kind of something that might look like this. So for bimodal distributions, you might have something that looks like, ooh. Doing the ooh. Right, so they might not be the same height. That was by accident, but that's okay. Okay, so here we have a bimodal distribution, right? Mode 1, and here we have mode 2. Okay. Anything more than two modes, we usually don't report it because it becomes really kind of useless, right? And so one thing to keep in mind if you have a bimodal distribution is that it's possible, not always the case, but it's possible that you've accidentally combined two groups that should be analyzed separately. Okay, and so that's why we want to keep an eye out for bimodal distributions. But then I'll highlight here, in multimodal cases, when there are more than two modes, the mode is almost never reported. Okay. It's also possible to have no mode, right? In that data set that I made up, there were no repeating values, and that's okay. So then we say that there's no mode, right? So that's a possibility as well, right? But the bimodal distribution is a little bit special, right? Because it is telling, right? Because we might have combined two populations or two groups that should be analyzed separately. So that's what I want to make a note of here. If we find that we have a bimodal distribution, it is possible, that that's not the case, right? So it's possible that two groups have been combined, but should be analyzed separately. Separately. Confession time. Separately. Anyone? Separately.
I say separately. Separate.
I don't know how old I am, but I still can't keep track of it.
Well, that's the English language. You know, I'm used to it.
Yeah, that's the correct spelling.
Anyways, I'm going to stick with this one. I'll look it up after. It won't help, but I'll look it up after.
Good thing this isn't an English class.
We'd be in trouble for sure. Or I would be in trouble for sure. Especially with some of my sentences. Oh man, time flies when you're having fun. Okay, that's enough about the mode.
Can I quote you on that?
Yeah. Time flies when you're having fun.
Yeah,
Yeah,
like
you bet.
while you're teaching a class. You like your job, that's a good thing.
Yeah. Yes, you may.
Okay.
Oh, and thank you, Karen D. Separately. Thank you. I think I spelled it right.
Yeah, it's spelled correctly. That's right.
So the last thing we'll see how long I blab about the geometric mean. But the last measure of center that I want to talk about, how about that? Yeah, exactly. Time flies when you're having fun. All right. The geometric mean is a different way of calculating the mean, right? The geometric mean, if we think about how we calculated the arithmetic mean, just the normal one, we add them up and then divide by the number of points, right? That's what we're used to doing. Now, with the geometric mean, what we do is instead of adding all the points up, we multiply all those points. But then instead of dividing by this number of points, we take the nth root, okay? And if you're doing the nth root on your calculator, you're going to have to raise it to the power of 1 over n, right? And this is not something that we're going to do by hand. Of course, Excel and definitely R calculates the geometric mean for you if you want it. But it's good to know the difference computationally. What are the differences between the two, right? So here we're multiplying each of the data points together, and then we're taking the nth root, okay? And so just to clarify what's going on here, we multiply all the data points together, then take the nth root, right? And they've shown it here, right? You might have to, if you're doing it by hand, you might have to raise it to the power of 1 over n, right? Your calculator probably has a square root button, but that's about it. I think this one, nope, not even this engineering one has an nth root button, I think. Has an nth log button. That's not going to help us today, is it? So then you take the nth root, okay? Notice that we use the same notation here. Wow. We use X bar, but then to show that it's the geometric mean, we use a little subscript G, right? And so here, whoa, it's because I'm so zoomed in. Use a subscript G to denote the geometric mean. Right, so like I said, the default mean that we're going to calculate is the arithmetic mean, right? Just the average, like we're used to calculating it, okay? If you find that you have to find the geometric mean, then you should denote it by a lowercase g as a subscript. Okay. When should we use the geometric mean, you might ask, or not, depending on what time of day it is, right? We should use the geometric mean if our data points, if they're not independent. So typically, if we have kind of stock prices day after day after day after day, then the geometric mean might be more useful, okay? And so, and the textbook has a really long example that I decided to cut because I don't think it's going to come up that often for us. And if it comes back up, then I'll bring it back up again. But usually it's just something we introduce and then we ignore it. So, but there is a long example in the textbook if you're interested, just kind of illustrating the differences between the two. And so we use the geometric mean, geometric mean as the measure of center for dependent data, right? So daily stock prices, for example, right? Day 1, day 2, day 3, those stock prices are dependent on the previous day, right? And so daily stock prices, for example, I feel like temperatures right? Daily temperatures, right? Or hourly temperatures if we want to mix it up, right? Our time measurement doesn't really matter, right? But hourly temperatures, things like that, right? So when you have this kind of dependency among your observations, then sometimes we'll use the geometric mean, right, as a more appropriate measure of center. Okay, just like the population mean with the arithmetic mean, then we have a population geometric mean, right? It assumes that we have the whole population, of course, but for us, we're just going to denote it by a mu lower and then subscript g to denote that it's the population geometric mean, right? You can ignore that probably, but it's good to have, I guess. All right, let's see. I think we'll leave this for next day. Okay, so we'll keep talking about just measures of variability, which is basically just measures of spread. And hopefully, I think we'll be able to wrap up the chapter next day. Not on Friday, because then I'm going to teach you guys some R stuff. So have your R ready. Or make sure you are ready. Anyways, if you have any questions, thank you. Here all night. If you have any questions, let me know. Otherwise, I'll see you guys on Friday. I'll stop this.
Bye.
Yeah.
Thank you. Bye-bye.
See you.